working. Hello, everybody. It is my pleasure to introduce Saurabh Gupta to you. Saurabh is a last year PhD student at UC Berkeley, advised by Jitendra Malik. His work covers computer vision, machine learning, and robotics. His PhD thesis is his work on visual navigation and perception, and that's probably what he's going to talk about today. Saurabh is the winner of the Google Fellowship in Computer Vision, Berkeley Fellowship, and he has won a couple of important challenges in CVPR, including RGBD, semantic segmentation, and captioning. With that, happy to have you here.
Thanks a lot, everyone, for coming. And today I'm going to talk about my work on visual perception and navigation in 3D scenes. But before I start, I want to briefly walk you through the history of computer vision. Computer vision started out as a discipline to enable robots to perceive the world. And this is evident from the fact that most early work in computer vision was motivated by robotic applications in mind, be it modeling images with 3D models or inferring the 3D structure of the world given multiple images. Not only that, but one of the first books in computer vision by Bertrand Hahn was in fact called Robot Vision. But in the 90s, computer vision researchers started to branch out, and the focus was on studying problems that could enable computer graphics applications. We figured out how we could stitch together multiple images into a single panorama and how to render people and places from novel viewpoints. But in the 2000s, computer vision researchers found yet another new buddy, this time in machine learning and big data. And computer vision researchers moved from stocking cameras to stocking hard disks so that they could download big data from the internet. Computer vision at this point has transformed into something that I call internet computer vision, where the dominant research paradigm is to download and label large-scale data sets from the internet and study them using sophisticated machine learning techniques to study a large variety of image labeling problems. And this has been a reasonably successful endeavor, leading up to algorithms such as maskRCNN, which can label complex real-world images such as this with the objects that are present in them. This naturally presents us with the question whether the current paradigm of internet computer vision is actually enough for Bertrand Hahn's robot to perceive the world. So let's actually see what can internet computer vision do for us. Given such an input image, internet computer vision can help us say what objects are present in this image. It can also tell us where these objects are and even precisely delineate the pixels that belong to these different objects. While this is great, unfortunately, all of this understanding only exists in the 2D image space. It tells us nothing about the 3D layout of the world. It does not tell us that this road actually continues behind these objects. It does not tell me that I can actually walk into the scene. It also does not tell me where would these objects be if I were to look at the scene from a slightly different viewpoint. And these are just some of the questions that a robot will need to have answers to if it were to successfully act in the world. Not only this, but internet computer vision is entirely limited to understanding the world from RGB images uploaded by people onto the internet. So here's a visualization from the MS COCO dataset, a dataset popularly used in computer vision, and in fact, the one that was used to train maskRCNN. And so you can see that a day in the life of maskRCNN consists of analyzing these interesting and photogenic images from Flickr. In contrast, let us look at the day in the life of a robot. Here is a mobile robot that is trying to walk around in office environments. And here is an armed robot that is trying to learn to grasp objects in clutter. Not only do these images look very, very different from the images on the internet, they are not, in fact, not images, but continuous streams of data. Streams of data that is determined by the robot itself through the actions that it takes. Moreover, because we determine what sensors we add onto our robots, robots are not constrained to just understand the world from RGB images. We can stack on extra sensors onto our robots, such as a haptic sensor to get these gel site images for more robust grasping, or add in LiDAR scanners on top of autonomous vehicles to obtain point cloud data for more robust, more safer driving. Thus, the current paradigm of internet computer vision only studies the narrow problem of 2D analysis of RGB images on the internet. And this forms only a very small part of the perception problem that a robot needs to deal with in order to act in the world. My research focuses on trying to bridge this gap between computer vision and robotics. And in this talk today, I'm going to show you 3 efforts where we have tried to bring computer vision and robotics closer. I'm going to show you how we can move beyond 2D image understanding and move towards 3D understanding of the underlying scene. I'm going to show you how recent advances in representation learning for RGB images can actually be extended to learn representations for very different sensing modalities that we may want to add onto our robots. But most importantly, I'm going to show you how we need to move beyond thinking of vision and robotics as 2 isolated modules and start thinking of them together and studying them jointly. And I'm going to do this in context of the classical problem of robot navigation, and I'll show you results for this. And in this particular talk, I'll first and mostly focus on the problem of navigation, and then give you brief teasers about how we can do 3D scene understanding and learning representations for varied modalities. So let's actually see what is this problem of robot navigation. So the specific problem I'm going to tackle is visual navigation in novel environments, where we have a robot that is equipped with a first-person camera, and it has been dropped into a new environment that it has never seen before. And what we want this robot to be able to do is to navigate around, which is go to a particular point in space or go find objects of interest. And obviously, this is a classical problem in robotics and has been very well studied over the last 40 years under simultaneous localization and mapping. So let's actually see what does a classical SLAM solution do for this problem. A classical SLAM solution will break this problem into two parts. One, that of mapping, where we want to go from the observed images to a geometric 3D reconstruction of the world. And second, that of planning, we want to plan paths from, in this 3D reconstruction from the current state to the goal state. And dividing this problem into these two parts has allowed us to make very large amounts of progress on both of these problems independently. We have sophisticated mapping techniques which can now take in inputs from various different sensing modalities to produce a geometric reconstruction. We also have sophisticated path planning algorithms which can now plan paths for various different complicated robot action spaces and so forth. However, this choice of geometric 3D reconstruction as an intermediate representation has some drawbacks. First of all, a geometric 3D reconstruction of the world is actually unnecessary for the task of visual navigation. Perhaps I don't need to tediously reconstruct everything that is there on top of this table in gory detail if all I wanted to do was to walk past it. But more importantly, a geometric 3D reconstruction of the world is also insufficient for the task of visual navigation. So here is a view from my office at Berkeley, and not many of you may have seen this image before, but we can very well speculate that there is this hallway that extends in both directions behind these cubicle walls. Thus, as humans, we can make meaningful speculations about parts of the world that have not directly been observed. However, a classical robot is constrained to only use information about free space that has explicitly been observed. Moreover, there are patterns in the way indoor spaces are laid out. Here is another view from an office at Berkeley, and if I were to ask you, how would you exit this office? You're more likely to succeed if you go down the first alley on the left, as opposed to the second alley. And as humans, we rely on our vast experience with similar other past environments to operate efficiently in a new environment that we are put into. In contrast, a classical robot throws out all of its experience with the previous familiar environments and starts mapping and planning in a new environment from scratch. And of course, there are navigational affordances. There's this notion that if you want to go to a very far-off location in a new building, you're more likely to succeed if you step out into this hallway. Or the fact that if you see a door, it can possibly be opened so that you can get into the room, and so forth. And these affordances simply don't exist in a purely geometric description of the world. Motivated by this, there has been a recent interest in studying end-to-end learning-based methods for doing navigation, where we set up a neural network architecture which takes in the current observation from the robot, along with a specification of the goal, and outputs actions that the robot should take in order to succeed. And now, if we have some supervision for what action the robot should take, let's say via reinforcement learning or imitation learning, these neural network policies can start picking up on some of the semantic cues that I was referring to in the previous slides. However, what is challenging to do with these end-to-end learning-based approaches is to actually use the structure of the problem. And there's all efforts that have tried to use neural network-based policies for navigation have only used very simple neural networks to model these policies. And this is actually not enough for the problem that we are considering. So let me actually show you a simple example as to why simple networks are not going to be enough for solving this problem. Let's say we have this image, and we want a robot that can go past this to the start location. So the robot is looking at this chair. It wants to go past it. Obviously, the sensible thing to do is to walk towards the chair and then turn around it and then go to the goal location. But let's actually look at in more detail what exactly happens in this particular case. So the robot has walked towards the chair. It is now seeing this chair. Let's say we are passing this through a simple neural network. And now the neural network realizes, OK, I should go around this obstacle. So it outputs an action that I should start rotating. So this is good. The robot starts to rotate. But by the time the chair actually moves out of the way, it has also moved out of the visual field. And now this neural network policy is confused. If I wanted to go straight, why am I rotating? And it would start rotating back. And now you might wonder, this is a very simple problem. You can actually just look at some previous frames, let's say 4 previous frames, and then that would solve this problem trivially. But then maybe this robot has momentum, or maybe this was a longer detour that the robot had to take. And now you're again faced with this problem that you cannot get to the goal location, that you will not be able to decide what action to take. Moreover, you're also throwing out all this precious experience with this particular environment, which may not be useful for solving this task, but would be useful for solving some other task that you may want to do in the future in this environment. And now you could argue that we can simply use a recurrent neural network, which can, in principle, keep track of arbitrary past information, but in practice can only keep track of tens of frames in the past, and is unreasonable to expect that can do complicated spatial reasoning and path planning. And in fact, I'll show you results which compare to this kind of a baseline. And if you look at even very simple animals like rats, they actually show fairly sophisticated mapping and planning behavior. So here are some experiments that Edward Tolman was doing at UC Berkeley 70 years ago, where what he did was habituated a set of rats to move around in this kind of a maze, where he would let in these rats at location A, and if they reached location G, they would get food. These rats very quickly learned that they have to go straight, turn left, turn right, and then they will get food. This is great. Next, what Tolman did was essentially modify the maze a little bit. So rats would still be let in at location A, but this direct hallway that they were taking to actually get to the goal location was now blocked. And now what these rats actually did was first, A, realize that this direct path was blocked, but then when they came back searching for how to get to the goal location, they actually picked the spoke which was directly in the direction in which the goal was there. And this led Tolman to conclude that essentially these rats are not showing low-level motor control behaviorism. They're not just mimicking low-level motor commands, which is turn left, turn right, but they're able to integrate their percept of the world into some sort of a cognitive map that allows them to do spatial reasoning and finding shortcuts. And this is kind of what we want to do here, where we want to take this rich spatial reasoning and so forth, which is prevalent in classical SLAM, and then unify it in some manner with end-to-end learning-based techniques such that we can also leverage semantics that are there in the real world. And I'm going to show you one particular way in which we have done this. We are going to train neural network policies for going from the image observation and a description of the goal to the final action that the robot should take. But we are going to build in insights from classical mapping and planning into the design of this neural network. In particular, this neural network is going to build up a spatial representation of the world as it moves along. We are going to use a mapper, which will take in these images to produce this spatial representation. And we are going to use a planner, which takes in this spatial representation along with the description of the goal to output the action that the robot should take. Once the robot has predicted an action, it will execute it in the world, it will get a new image, and then we'll repeat this process. We'll now again feed in this image to the mapper, but in this case, also take into account the spatial representation from the previous time step and the relative pose between the previous time step and the current time step to output an updated spatial representation. This again goes into a planner, which outputs the action the robot should take. And this keeps on going. Now you might wonder, how is this any different from a classical mapping and planning-based solution? The crucial distinction over here is that both this mapping and planning function are actually implemented as differentiable neural network operations. And what that allows us to do is to essentially jointly train them for the end task that we are carrying. So we can actually train a mapper and a planner for the end task of doing visual navigation. And what this allows us to do is to move beyond simple representations for spaces. So as I was mentioning, in a purely classical world, the representation for space is a geometric version, which is, let's say, where is free space and where is no free space. But once you set up this as an end-to-end learning problem, you can actually move beyond this simple representation for space. You can actually go to more expressive representations for space, and that can be learned in context of the task that we want to do. So let me tell you a little bit more about the spatial representation. So we are concerned with ground robots over here, which have wheels, and they are going to be moving around in indoor buildings. So we are building up this spatial representation in a top-down view. So this is going to be a top-down view of the environment, where each pixel in this spatial representation is now going to correspond to some part of space, physical space. However, we are going to let the neural network decide what representation it wants to capture at that particular location. So it can write out these vector-valued feature vectors corresponding to each spatial location. We're also going to maintain not just a feature vector, but also a confidence, which is how confident are you about the information that you're storing at that particular location. We also need to decide a coordinate frame in which we are maintaining this representation. And that choice is essentially we are going to assume that the robot is always going to be in the center of this representation and looking forward, looking upwards. So essentially, we are maintaining an egocentric bird's eye coordinate frame for maintaining this spatial representation. Now, let me tell you a little bit about the mapper. So as I said, we are going to incrementally build up a representation for space. So let's assume we have some representation for space from the previous time step. And now we have this new image along with an ego motion that comes in as input. What we first do is essentially transform this representation of space to bring it into the current coordinate frame. And this can be done by a differentiable warping layer, which is essentially doing bilinear sampling, which is obviously differentiable. And what exactly happens here is if the robot is rotating right, you essentially copy over the representation and then rotate it left. So that now, again, you are at the center looking upwards. And now, once you have this representation, now you start using information from the current image. And you pass it through a standard encoder-decoder network, which takes in the image, this first-person view, and then transforms it into a top-down view of the environment. And you make a prediction, and then you essentially combine these two predictions to produce an updated spatial representation after having taken into account the current observation. And now note here that maintaining this in an egocentric coordinate frame allows us to simply learn this encoder-decoder network. So this encoder-decoder network can actually say, OK, I'm standing over here. I'm seeing a hallway. And it can paste in this hallway-like pattern in its map very easily. So this makes learning much easier. So this is essentially the differentiable mapper. Let me tell you a little bit about this differentiable planner. So our differentiable planner is essentially based on this classical idea of solving a planning problem by Bellman in 1957, which is essentially value iterations. What we want to do is to essentially estimate a value. How good is it to be in a particular location if I want to get to a given specified goal location? And what value iteration does is essentially it's an iterative algorithm to compute these values of different states. And intuitively, how it works is that you want to get to this dot location. This is the goal location. So obviously, the value of being at the goal location is going to be high. What that tells you is that being around the goal location is also good. So the value of being around the goal location is also high. And now you can use these one-step dynamics to actually propagate this information about where the goal is over space. And you get some behavior like this, where you have this kind of a map, brushfire-like map around, which tells you about how to get to the goal location. And now if you observe this computation, essentially, let's say we want to compute the value at this green location. What all we need to do is to actually look at a local neighborhood around this location, and then look at what are the previous values that I've computed over here, what is the topology locally in the environment over here, and then you can paste in the value that should be there at that location. So all of this computation can actually be done locally using convolutions and max pooling. It's a particular kind of max pooling, it's standardized max pooling. And now what this gives you at the end of the day is essentially these kind of value maps, where the local neighborhood of values around your current location tells you what action you should take in order to get to the goal location. And again, remember, we were maintaining this representation in an egocentric coordinate frame. So you do this process, you get the values around the center of the image, and you can read off what action the robot should take in order to make progress towards the goal. So this is essentially the differentiable planner. And again, I'll recap that we have this end-to-end trainable neural network, which can now learn spatial representations for the tasks that we are going to do. Yes?
So in the training, you're doing separate training for the differentiable mapper, and then at the end as well, or?
It's all being trained jointly. So during training, so let me actually say a little bit about policy training. So we are training it in a supervised manner. So there's an image coming in, and there's an action that you want to predict. And we have assume access to what the right action is, and we're training this entire network end to end.
So could that potentially give you worse mapping in the middle?
Yes, so the target here is not to get good mapping. That is not the goal of this work. The goal of this work is essentially to come up with policies that can act in the world. That's why we don't necessarily care about what representation the mapper learns, as long as it can actually solve the task. And I'll show you, but we can actually tease out what the mapper learns, and I'll show you that a little bit. So let me elaborate on this policy training. So what we did was essentially construct a simulator which is based on real-world scans. So there are these scans of indoor buildings that are available. You can actually use them to construct a simulated environment in which you can try out some of these policy architectures. And once you have these kind of simulated environments, you can actually compute what is accessible space, what is traversable space, and so forth. And you can set up learning problems in this kind of an environment. So you can say, OK, I'm going to initialize myself here. I want to go to this other room. what are the optimal actions that the agent needs to take. And that's how you can generate supervision. And that's where we get the supervision for this action that the policy should output. And now we can train this entire policy in an end-to-end manner for taking the right actions. So let me show you some results. So again, these are results in simulation. What we were interested in was this generalization behavior. Remember, I wanted a robot which I train in some buildings and then bring it to a new building, and it should be able to work. And that's exactly what we're trying to test over here. We have trained it on building 1 and 2 in this particular scanned setup, and now we are testing it in building 3. And what the robot is going to see is essentially the image that you are seeing on the center of the screen. And what I'm also showing you on the bottom right corner is the trajectory in the top view. And now note that this is purely for visualization. This is not being input to the network, to the policy. And in this case, the robot wants to get to this green star location. And let's see actually what it ends up doing. So it conveniently walks out of this room into these hallway-like things, turns around in this hallway, goes around the corner, continues to walk, and then finally is able to get to the goal location. Yes?
So does the robot at every point in time know its location also during the mapping process, or?
Yeah, so in this case, remember this ego motion that I was saying that is being input to the network? So that ego motion in this particular case, because in simulation, we have assumed that we know precisely what the ego motion is. So that's why it's able to maintain these consistent representations. I'm going to show you a little bit at the end where we have tried to relax this assumption, and I think that will address some of the questions. So as I was mentioning, people have used learning-based policies for navigation. However, because they have used simple networks, their policies cannot actually do backtracking very effectively. However, our policies can actually do backtracking. So in this particular case, again, you want to get to the star location, and what will happen is this robot will actually not realize that that location is in a different room. It will try to go on the room at the bottom. It will realize that there is no path from over there to the goal location, and then it will come back and be able to get to the target location. So here is what happens. So it wants to go to a room which is towards the right, but it walks into this room which is below it. It realizes that's not where it wanted to go. So it starts coming back out and then going back into this different room to actually get to the goal location. And then here's another example where essentially the same thing happens. You are in this hallway. You want to get to the star location. Because it's a new building, you have never been in this building before, you make a mistake that, okay, you go into this room expecting that this point would be over there, but you realize that you're not, that is not the case. So then you can actually come back and then go into a different room that you can actually succeed with the task. So these policies can actually start backtracking because we have built in this kind of reasoning behavior inside these neural networks. We can also look at some of these results quantitatively. So for example, what we are doing is essentially measuring success rate, which is the goal is sampled to be about 32 time steps away, and then we are running the policy for 40 time steps and seeing whether it gets close to the goal location or not. And I was mentioning before, these reactive policies don't really work very well at this task because all they can do is essentially memorize the training environment. So they work amazingly well on training environments, but they cannot actually generalize to these new environments that you put them into. LSTM-based memory units actually work somewhat better, but then our method actually is able to outperform that. We can actually, because these are neural networks that we are training, we can use RGB images as input, or we could use depth images as input, and it's a convolutional neural network that you train, and you can actually see that the same trends continue. But of course, performance is better if you start using explicit shape as input. And we are also able to make a comparison to a more classical method over here, where we are constraining this map to only reason about free space that is available from the observations that the robot is making. And as you can see that this works less well in these kind of situations. Again, we were focused on the question of generalization. So we trained these policies in simulation on these office environments, but then we can actually test it on these home environments, which are also available as scans. And you can see that the robot actually does shows reasonable behavior in getting to the target location. Yeah, there's a particular way this data is acquired, and that's why there's a rich people bias over here, but let's not get into it. So what I showed you results was when the goal was being specified geometrically, which is I specified, okay, I want to go to this delta x, delta y location. But now because these are policies that we are training, we can actually we can just change the way we are specifying the goal. So let's say we don't want to go to a position in space. We want to instead go to a semantic target. Let's say we want to learn a policy that can actually go and find chairs in environments. And now essentially we retrain these policies with this kind of a goal specification, and we get a policy which can actually now go and find chairs. So again, in this case, we are going to I'm going to show you results on novel environments that the agent did not see during training, and this is kind of what it does. So these are, again, in these office environments. So it will miss out on a few chairs here and there, but then the general policy is it will go inside a room, that's where chairs are, and then once it sees a chair, it will stay there and start rotating, declaring that it has figured out that it has found a chair. Here is another example where it is going down a hallway, and it decides to go into a room so as to find a chair, and then once it gets there, again, it will start rotating. Here are some examples on these home environments where, again, you can actually walk around and find chairs and so forth. Again, this policy was just trained entirely on office environments, but it shows reasonable performance on these home environments that we put it into. Yes?
What's the supervision for this level?
So the supervision for this task is essentially you want to take an action which reduces your distance to any chair in the environment.
And you have semantic segmentation.
Yeah, so you know where the chairs are in these office environments, and then you can generate this kind of supervision. Now, so this is good. I think I've showed you that these methods perform reasonably in these environments. But you can start asking the question, what does this mapper actually learn? And so what we're going to do is to essentially try to read out whatever information this mapper has learned over time. And the standard way of doing this in these deep network models is to try and train readout functions. And let me explain what that means. Essentially, we have trained this network. We have now frozen all of these parameters. And now what we are going to do is to run this policy on a new environment, and then look at the activations of the mapper. And then we are going to try to predict. Okay, we're trying to train classifiers where we are trying to read out different properties that the mapper exhibits. So for example, one might think that, oh, this mapper should actually at least capture free space. That's kind of what we started out with. Is it actually able to capture free space? And note that in all of these experiments, the gradients are not going to flow back into the neural network. The gradients are only, it's a pure readout function on top of the activations that the network is getting. And so this is kind of what we did. We have trained this readout function, and now we are testing it in a new environment, which neither the policy nor the readout function was trained in. And what you can see is essentially you are inside this particular room, but you can make a prediction that there is free space outside in terms of this hallway. You can actually make a prediction for parts of the scene that you're not directly observing. And this is what I was motivating this particular work with. So we can actually let this policy run a little bit. So now you are stepping out in the hallway. Actually, I should mention the dot in the center. Again, remember, the agent is always going to be in the center looking upwards. And that's kind of the coordinate frame. And you're always seeing this egocentric prediction. So this agent is now going to move forward. And now it turns around. And now, again, note that you are seeing this doorway on the left. And you are able to make a reasonable prediction that, oh, there is free space going to be in that direction. Even though you have not observed, you have not been into that room to actually make a prediction. So you see this kind of free space to the top left corner. Now, you could also ask, does this mapper representation learn anything more than free space? So free space is something that we already knew that it would be useful for navigation. So what we can do is essentially train these readout functions for different for other things as well. So what we did was essentially train a readout function to predict whether you are in a hallway or in a room. And these are now concepts that are not just representing free space. So what I'm going to show you is a prediction, again, in the same coordinate frame, you're at the center looking upwards, but I'm going to show you not just the free space, but also predictions for where it thinks the hallways are, where it thinks the rooms are. So this is the current view. It has made some predictions, and then it will start walking into a room. So at this point, it's starting to walk into a room, and you can see that it is able to predict that this hallway will finish, and then you will end up in a room. So there is a blip that you see in the prediction for where the room is. So we can actually we can see that this representation is actually richer than what we could have handcrafted, and this is useful. What we've also done recently is essentially deploy some of these policies on a real robot. So here we have a TurtleBot, which we are going to, we are just using the RGB camera from over here. We are ignoring the depth sensor. And it has been put into this building. This is now a building at Berkeley. So remember, those meshes were coming from actually scans of offices in Stanford, and now we are going to test it in Berkeley. And so we have set up this kind of a maze where we have these chairs. And what we want this robot to do is to move forward 5 meters. And so I'm going to run this policy for you now. And what you see is it's actually able to go around these chairs, avoid running into these chairs, and then get to the goal location as desired. Here is another example where this robot is now actually trapped inside this cubicle because of this chair that is out there, which prevents it from just taking the simple shortcut out. And you'll see some amount of backtracking behavior over here, where it goes into this particular corner in the cubicle, realizes that's not where it wants to go to, then come out and then turn to the right, and then that's where the robot wanted to actually go. So this is useful. And what I've showed you essentially is how we can operationalize insights from classical mapping and planning into the design of neural networks. So what you can see is that we have made mapping somewhat implicit into the network. We are not training the network for doing mapping. We are training the network to take the right actions in the world. But then but we have built in this construct for doing mapping as it is trying to solve this particular task. And this has allowed us to go from handcrafted free space or obstacle maps to actually learn task-driven semantic maps that capture more than just free space that we knew about. We can perhaps play the same game with other kind of tasks that we may want to do as we are solving, as we are moving around in an environment. So there's this problem of localization, which is, let's say you have some experience with the environment already, and now you are put in this environment again, you want to localize where you are. And again, in robotics, we have come up with sophisticated techniques which can do this kind of localization. And now perhaps what we can move towards is essentially an architecture which takes in this map or your prior experience with the environment and the current image, and then implicitly tries to localize itself in this map such that you can output the right actions that the robot wants to take. So we can set up this kind of a neural network. So I won't go into too many details over here, but what we have done here is that we have a familiar environment where we know we have some past observations that we have made, and we want to go from one particular location to another location. So we have planned a trajectory. And now what we do is essentially compute a description of this trajectory in terms of the images that it is going to see along the way. So we speculate what you're going to see as you're walking along this trajectory. You compute a path description along this. And now what we have is essentially a controller that is trained to localize against this description of the path given the current image. And now if it localizes against it, it figures out what information it needs to take out from that path description to take the right action in the world. And thus what you can see is essentially over here, localization is now being built into this neural network as something that it has to do so as to take the right action in the world. So here's a video. Again, this problem only makes sense if you have noisy actuation, so you don't exactly know how you moved. So we are simulating over here a very simple way in which the agent actually executes an action, but that action fails with some probability. So it actually wants to follow this blue trajectory. What it ends up doing is following this red trajectory. And here is exactly kind of what happens. So blue is the trajectory that it wants to follow. What it ends up following is this red trajectory. And what you can see is essentially, again, there are these common sense patterns that, okay, if you were going forward, you will want to go through a doorway rather than just bumping into the doorway. So you can be robust to these kind of things if you start expressing some of these plans in a more semantic manner. So far what I've shown you is essentially navigation in the static world. But unfortunately, the world is not static. So for example, here's this robot that is trapped inside this cubicle, and it is trapped because there is this chair in front of it which needs to be moved out of the way in order for the robot to get out. And now, again, this requires you to come up with a policy which can figure out that this chair needs to be moved out of the way. And in computer vision, we have a large history of figuring out how do we deal with objects. So we have sophisticated techniques for doing object-centered reasoning. In particular, we have object detection, which can actually detect a lot of these objects in these images and so forth. But as I was alluding to in the beginning, all of this understanding about objects is in the 2D image space. It does not tell you where are these objects in the 3D space and so forth. And that's what we have tried to do in order to get from this 2D image understanding to essentially a 3D scene understanding, where the first attempt is, obviously, you might wonder that you can use these shape sensors. While these shape sensors are great because they give you not just the color image, but they also give you a depth image, which is how far is each pixel in this image in the 3D world. And while this actually allows us to improve performance at a number of standard computer vision tasks, let's say detection and segmentation, they actually don't quite give us the entire answer of how the 3D world looks like. In particular, they only tell you about parts of the scene that are directly visible. So here is this image. You are seeing the image and the depth image. And now you can actually start rotating this image. And then what you see is that you actually don't quite see this chair in entirety. You're just seeing like only a very small part of the chair seat and so forth. And this is not, so even if you use a depth sensor, it actually does not give you the full answer of what is the shape of the world. And, but what you do know is essentially how do chairs look in general. So you have access to, let's say, from your prior experience, you have access to actually, a chair has a seat, it has a back and so forth. And what we can do is essentially use the partial shape information that is available, let's say via these depth sensors, to actually align these full 3D models to the data. So you can actually say that, okay, I know about chairs in general, and now I'm going to try to align a general chair model to the data that I'm seeing to be able to make predictions about parts of the scene that are not directly visible. So this is a simple alignment problem that you can solve. And if you do this, you can actually now start making predictions which are not constrained to just the 2D image space. You can actually start being able to replace objects in place by 3D models, which can allow you to make predictions about parts of the scene that you're not directly observing right now. So in this case, you can actually say that, oh, there is this chair, it has a seat. Even though you're not seeing the seat, you can make a meaningful speculation that there would be a seat and so forth. And while this is good, this relied on alignment-based techniques. What we have also done more recently is essentially do full 3D inference via prediction, where you can actually train convolutional neural networks to actually go from image observations to not just the category that the object belongs to, but also more detailed attributes. Where is this chair in the real world? What is its size? How is it oriented? What is its precise shape? And so forth. And you can also make predictions for scene surfaces. And what this allows you to do is not just do it with RGBD image observations, but you can also do this with vanilla RGB images on the internet. And here are some visualizations of what this does. So you have this image as input. You can actually make a full 3D prediction about the scene, where you can actually now answer some of the questions that I was alluding to in the beginning. You can actually walk into the scene. You can answer the question, how will the scene look if I were to look at it from a different viewpoint? You can actually remove these objects and infer that, oh, there were these walls and floor that were there behind these objects. So you can make these predictions for what is behind the object. You can actually reason about occluded parts of the object. You can actually infer that this table was occluding these parts of the chair. And this chair, if you remove the table, will look something like that. And you can also start moving some of these objects around. So again, I mean, this is some steps towards going towards a 3D understanding of the underlying scene, as opposed to just a 2D understanding, which is common in internet computer vision. And all along, what I've shown you is essentially there's utility to extra sensing. So I showed you this in context of navigation, where if we use a depth sensor in addition to the RGB image that we are seeing, you get improvements in performance. I showed you the same thing for recognition tasks. If you have a shape sensor, if you have a depth sensor and you're using information from the depth sensor as well, you actually get improvements for standard tasks of detection and recognition and segmentation. However, this is somewhat challenging because there is not that much depth data that is out there to learn models from. So here is a histogram of the size of a typical image dataset. So the largest depth image dataset is going to be many orders of magnitude smaller than a typical RGB image dataset that is used in internet computer vision these days. And this is not just the case with depth images. This is also the case with any kind of additional sensors we want to put onto our robots, be it LiDAR scanners, thermal scanners, sound or haptic scanners. And this naturally presents us with a question as to how do we learn models on these kind of modalities. And this especially comes up in context that the current paradigm for learning representations relies very heavily on labeled data. So here is a recipe for solving any computer vision task. You essentially pre-train a representation on large data set such as ImageNet. And then what you do is you fine-tune this representation for the target task that you are concerned with solving. Now, what is the paradigm in which we can learn features for these extra sensing modalities that we will want to add to our robots? And for this, what we have come up with is a technique for stealing supervision from modalities that are very well labeled to now transfer some of that supervision to modalities that are not so well labeled. And this is based on this observation that mid and high-level layers in a CNN are actually semantic. So if you have a convolutional neural network and you have trained it on a data set like ImageNet, you can start asking the question, what does the intermediate layers of this neural network like? And what it turns out is that they actually like semantic things. So it will, for example, fire on parts of faces, parts of dogs, parts of monitors, and so forth. And now what you can do is you can use this observation to actually transfer models between modalities. So let's say we have some paired data. Let's say we have a robot which can walk around with these two sensing modalities, and it can record paired data, where you have the RGB image and the depth image of the same scene from different viewpoints. And what now you can do is essentially set up a learning problem where you extract out the semantic description of the scene from the RGB image that you were seeing, and you can use that as a supervision to train a model on a new modality that you did not have as much labeled data for. And now you can do this with standard techniques like backpropagation, and you can learn these kind of models on these modalities. And as the paradigm becomes, you can continue to pre-train your representations on well-labeled modalities such as RGB images. We can transfer the supervision using an unlabeled but paired modality dataset, where you have both RGB and depth images. And now you can start using this representation for whatever task that you have in mind. And I'm not going to go into details, but this representation actually works reasonably well on a number of tasks on depth images and so forth. And what this also gives you for free is essentially aligned multimodal representations, where you have a particular neuron which fires on, let's say, parts of beds. You can actually now, you have the same neuron, which you look at it on the paired modality side, and it also fires on parts of beds. Here is another neuron which fires on parts of chairs, and the same neuron actually fires on parts of chairs on the depth side as well. And what this can allow you to do is to transfer detectors that are trained on internet data to actually work on these additional sensors that you have on your robots. So for example, you can take a detector that was trained on Microsoft COCO dataset, again, the dataset typically used in internet computer vision. You can actually think of the detector as comprising of a feature extractor and a classifier. And you can take out the feature extractor, do this supervision transfer using a paired but unlabeled dataset, and now you can plug it back in to get a detector that can work on a new modality that you may want to use onto your robot. And in fact, this work has actually been extended to other kind of modalities where people have been able to transfer models between just images and panoramic images, images of different images and thermal images, images of different qualities, and also transfer models between shapes and images, and in fact, also transfer models to some modalities like sound, and also transfer models to translate between different languages. So what I've shown you today is essentially, as we start thinking about computer vision and robotics together, we realize that we need to move beyond thinking of 2D isolated images of the world that are made available to us. And we need to figure out how we can analyze continuous streams of multimodal data that is coming in. And I've shown you techniques as to how we can start using some of these, how can we extend computer vision techniques to start using continuous multimodal data. And while this is some first steps towards this direction, there's obviously a lot more to do. So for example, I showed you work on how do we move around in the world. I showed you work on how do we obtain an object-centered understanding of the world. And a very natural next question is, how can we make this understanding of the world actionable? How can we go from this understanding of here's a chair to actually coming up with policies which can move these chairs out of the way if the agent wants to do so? How can we actually have this emerge through a learning process? And as we think about mobile agents, they will not exist in the environment by themselves. They will have to coexist with other humans and other mobile agents. And again, in computer vision, there is a rich literature on how do we do action recognition, how do we analyze what humans are up to, and so forth. But then again, the question is, how can we make this understanding actionable? How can we use what computer vision system, whatever we understand about humans and their actions in a computer vision, but make that understanding actionable? How can we take better actions knowing what the human is actually doing? And of course, I used navigation as a test bed to figure out connections between vision and robotics, but manipulation is no different in the sense that perhaps there is room for such structured models which have some kind of 3D reconstruction and planning baked into them for the task of manipulation. Maybe we need to figure out, okay, how can I move something out of my way if I have to go and manipulate something that is behind an object? There is scope for doing manipulation in context of other humans, and how do we infer their intentions and so forth. And hopefully, some of the things that I've talked about today could possibly apply to problems such as manipulation and so forth. But it's not just that. I think there is information flow from robotics to computer vision. And here's a simple example. So computer vision right now relies very, very heavily on using human-labeled data for training models. And I mean, that's just the way things are done. But perhaps this is the case because we are thinking about vision as isolated images on the internet. And maybe we require much less supervision if we think about vision in context of an embodied agent that is living in an environment. So here is an example. Here's a very concrete instantiation of this idea, which is, let's say I have a robot which can detect chairs when it's close by. And now if it is on the internet, if it does not recognize a chair, it doesn't have anything better to do but to ask a human. But let's say in this particular case, this detector fires that, oh, there is perhaps a chair over there, I'm not really sure. Now what this robot can do is essentially start walking towards this chair. And as it is walking towards this chair, at some point, its chair detector will start firing that, I'm actually confident that this is a chair. And now you can actually propagate this label back in time and say, OK, all of these things that you saw along the way are actually chairs. And there's just one example as to how, when you can interact with the world, it is possible to think about computer vision in a somewhat different light than what it is being thought of right now. And it's not just these kind of things that we already do in computer vision. But in computer vision, because we are constrained by humans to provide us labels, we are not able to study tasks for which humans are not good at providing labels. For example, about physical properties of the world. I want to figure out what is the coefficient of friction for different things. I want to figure out Young's modulus, Young's coefficient of elasticity. And humans are not good at producing these labels. But what we can do is we can instrument our robots with extra sensors, and as they move around, they can poke at things and build up a data set of how are these physical properties of the world. And maybe that would be useful to scale up perception models for things that we cannot actually just do right now. So hopefully what I've shown you is essentially how when we think about computer vision, not as an algorithm in the internet, but as embodied agents, interesting challenges come about. How existing vision techniques can be used to solve some robotics problems, how robotics can actually help computer vision with some of the things that we are trying to do. And I think this is an exciting time to be working at the intersection of computer vision and robotics. And I think in the future, this will emerge, these two fields will converge into something that I'm calling embodied computer vision, and where we will actually go back to the pre-90s era and start collaborating with, have more intimate interaction with robotics people and making progress on AI together. And this is not just a case about computer vision. I think more generally, fields in AI need to come together to solve problems at the intersection. So I showed you some of my work, which is at the intersection of vision and robotics. I also have some work at the intersection of vision and language, where again, it's the same theme. We don't want to think about language in isolation. We want to think about language as grounded in the real world. And we have only done this in context of language and vision, which is we have grounded language in context of images. But I think all of these are scope for future work. And with that, I'd like to thank my collaborators, and I'm happy to take any questions.
So we have time for a few questions. If not, I'll ask one while we're waiting for the rest. So at the beginning of your talk, you sort of implied towards these implicit models of space. And then in the second part, you move to more explicit parts. So what do you think is the right representation for navigation and then moving towards manipulation? More explicit or implicit?
Right. So I think that's a great question. So what I showed you is I showed you explicit representations for more sophisticated tasks. So if you did not care about moving a chair, there is no reason to express it as an object. But when you want to start thinking about this, okay, maybe I need to move this chair out of my way, then you need to figure out what is the right architecture for capturing those things in. And I think right now, the solution that we had is, okay, you will build in the notion of objects. So we have figured out machinery of how we can do that with neural networks. Now the next step is actually use it in context of a policy and then figure out how can that work. So I think there is this question of how do you design architectures, and then there's this question of how do you use that architecture for a downstream robotic task. So I think both have to be done, and we are at different points in time with respect to these tasks. Yes?
Do you have a specific goal in terms of robotics? Like you want to create a robot that does X?
Yes. So the question is if I have a specific goal for what a robot should do. I think the problem that I want to tackle in the near future is mobility, which is have robots move around in real environments, in new environments that they've never been in before, and make them robust and so forth, and study some of these tasks that I was mentioning. How can they coexist with humans? How can they interact with objects in the world, and so forth?
That's not really a task. That's more like a capability, right? So you did mention autonomous driving, for example. That would be like the obvious.
Oh, I see. Yes. So I think home robots. I think that is kind of what I am interested in right now. And I think because low-level control and actuation and so forth is very well worked out for these things, it's plausible that these can come into the real world in unstructured environments and so forth. Environments that change, environments that have people in them and so forth. and the like. So I think that is what I will like to go after in the next few years.
Maybe also related to Ali's question about the representation. So you're still, as the underlying representation, you're still focusing on this 2D grid representation, right? And that is kind of what the traditional representation that people have been using, and it comes with all these additional problems that now you need to come up with a spatially consistent representation, which means if you would consider uncertainty during the mapping process, it's really hard to build these consistent maps and things like that. Now that you're using vision and you're also using more semantic representations, do you think that trying to build these grid-based representation is even the right underlying model, or should it just be landmarks, or what should we do?
Exactly. So I think so the first work that I presented in more detail was actually explicitly getting at this notion of space and so forth. But in subsequent work, we have realized that, okay, as an agent moves, it's hard to maintain these representations. And what may be better to do over there is have more landmark-based representations. And the policy that I was showing you, which is figuring out, okay, here is a path that I want to follow, and here's a controller which tries to execute this, is actually trying to get at that notion. There is some scope for still doing spatial reasoning because you want to figure out these shortcuts and so forth, but maybe that doesn't need to happen at that kind of a time scale, that kind of a scale. So I think we'll need to do both, is my short answer. And classical robotics does both of these things as such already, right? So the question is, how can we do this with learning so that we can actually incorporate more and more of the semantic information? So again, going back to the localization example, a very reasonable description of a policy is, I want to exit this room, go down the hallway, and turn right into the last room or down the hallway. And now that, actually you don't need any localization, right? You can actually just open loop, you can just execute that under a feedback controller and it should be fine. And I think that what I showed was one attempt in that direction, but I think it's not done yet, of course.
You have a paper and you showed a little picture there about aligning 3D models to the depth data.
Yeah.
And you're showing kind of very simplified 3D chair models. And I remember a few years ago at CVPR, someone had like a database of every possible chair anyone had in the whole world. So part of my question is, you showed a lot of different kind of chairs, including fancy living room chairs. Can you really align these simple chair models? And then taking it a little further, a long time ago, there was a PhD dissertation on representing chairs and other objects by their function. That was when we first got depth data. And this person was saying, well, a chair, it has to have a sort of horizontal surface and a vertical back, and the horizontal surface has to be so far from the ground so it's sittable. Are your networks learning any kind of structure and function of the objects?
Right. I think that's a great question. So where we want to go with this work is essentially embed them in an actionable manner. And if the action involves being able to reason that you have to sit on them, then these things should emerge. You also mentioned there being a very large number of models that are available. Again, I think it depends on the task that we care about. If we care about the notion that you can actually sit there, then even a coarse model is reasonable, as long as it is able to make a prediction that where the seat is. Now, it might not match the precise geometry elsewhere, but I mean, again, if it is for a graphics application, then I would think of it differently. If it's for a robotics application, I might think of it differently.
We'll do one last question.
So I'm interested in neuroscience, and there's, maybe you've heard about grid cells and place cells.
Yes.
So I'm just sort of curious, your representation was egocentric, and it seems like place cells in a mouse, for example, are very absolute in their position. So these cells will fire when you're in position X, Y, but does like absolutely in that position. So do you think if you train this in a less egocentric manner, would those emerge from your training?
Yeah, so I think the choice of coordinate frame in our particular case was just was essentially an engineering choice in some manner, because it makes learning much easier. You could also equally easily express an allocentric version where you are maintaining the map in a fixed coordinate frame, and then you are moving where you are pasting information into that map. I think that is possible. I'm not trying to make a claim one versus the other. I mean, there were some attractive properties that, you're representing space in your local neighborhood in much higher resolution as opposed to things far away. So you get all of these properties for free with egocentric representations. And that is what that is what motivated art choice. I'm actually not entirely, so there is this notion of place cells and grid cells, but I think you could do other behavioral studies to figure out whether you are maintaining the distance to walls and so forth from your current location or not. And I'm not entirely an expert in this area, but I've seen some recent work from Liz Pelkey, where they were trying to say that, okay, some of these things are expressed in an egocentric coordinate frame. So I think it'll be interesting to look at all of that literature and context.
Thanks a lot. Let's thank the speaker one more time. If you have questions, see him offline.